Okay. So, hello everyone. Let's get started. Just can anybody just confirm once again that I am audible? Okay, great. So today we will be learning about processes. And before we get into that, let's have a quick recap of what we did in last lecture. So we discussed what is kernel mode and what is user mode. We again discuss what do we mean by mode bit, and then again we got a little bit of introduction to system calls, how system calls works, and how exactly the mode bit changes when a process makes a system call, and how exactly the mode bit changes back when the system call returns. Right. So first, before moving to that, any doubts in this? Any point you guys want me to repeat? Okay then. So if there are no questions, then we can move ahead. Let me know if you have any doubts, right? Okay. Can you write your question maybe? Oh. Don't know
Good
why
evening,
this.
sir.
Hello. Yeah.
Yes. So my doubt is from second lecture slide number 31, there was a question and my doubt is between A and D option. The doubt is that what is the difference if we say that kernel is running and CPU is in kernel mode?
Okay. So question is basically this. What is the difference between? So I don't know what question you're talking about. So I have to open those slides again. But what I understood is basically this. What is the difference between kernel is running and then second thing was like CPU is in kernel mode, right? So what is the difference between that? That is the question, right? Okay. So assume first of all, let's understand this statement. When we say kernel is running, so first question is this: what do you mean by kernel is running, right? It basically means that the code of the operating system is being executed by the CPU. Okay, so whenever we say kernel is running or some process is running, it basically means that the CPU at that particular moment is executing the code of that particular process or that particular program. So in this case, the kernel is running. So operating system code is currently running on the CPU at this one, right? And then second thing is like CPU is in kernel mode. What this basically means, so what this basically means is that the mode bit in hardware is currently set to privilege mode. Whatever, that's pardon my spelling. Okay. Yeah, mode bit is 0, whatever, right? So this is what we mean when we say CPU is in kernel mode, right? So here it's basically it's a hardware kind of like configuration. When we say CPU is in kernel mode, it just means that that bit is basically set to 0. That's all it means, right? While when we say operating system is running, it means that the CPU is executing operating system, right? Is this understood? Okay. So now there is a little bit of a catch here. So the way we have designed this complete system, right? We said that there is user and then is kernel or operating system here. And here we say that this is what only the critical instructions should be allowed only in this OS section, right? Or OS mode or kernel mode, right? Critical code. That's what we meant, right? That was the design that we had last time. So anything which is critical code, or maybe I should call critical instructions, all those critical instructions should be run in OS only, right? So it means that whenever we want our OS code to run, the mode bit should be 0. Okay, that's what we want. This is our design. This entire thing is our design. Okay, is this understood? Okay. So in this particular design, whenever operating system is running, the mode bit will be 0, right? This is by design. This is our design. Whenever operating system is running, the mode bit equal to 0, right? So in some sense, when we say that CPU is in kernel mode, it means that operating system is also running in some sense, right? In some sense. But there can be some corner cases. For example, this some interrupt comes in and then it executes some generic code, which is kind of like some fixed code or something. Or maybe there are some cases when like you have some different kind of code, like some device drivers or something that actually get executed, which is not actually the part of operating system, but they are added as a add-on features, right? So not the part of the original operating system, but you add it later. Like device drivers are like that. But it is safe to assume that when we say in most of the cases, whenever CPU is in kernel mode, it is executing some part of operating system. So exact difference is this only. But as per our design, they have this relation. So CPU is in kernel mode, it means that kernel is running. Is that understood? This is for by our design only. I hope that is clear, right? So there was some other question. Just 1 minute. So how can I access the program counter if it is only one way to main memory or address bus? Suppose if you just restart, and how the program counter. We will get to that in when we today we'll first discuss this system startup only. I'll discuss this point there. Sir, does the kernel run all the time? I was reading Galvin's slides and it was written that kernel program is running all the time, but the internet does not seem to be agreeing with it. So what, yeah, again, the question is, what do you mean by running all the time, right? So when you say is kernel running all the time, right? So I guess we discussed this yesterday also. Running all the time, right? So we had this example yesterday, right? So where we had a single CPU, there was single CPU, and we had this memory. There was some part of this memory where operating system code is there. This is operating system code. And then there was a process. And the process code was here. Or program code, whatever. And we said that at a given moment, CPU is executing the program. This is what we said. So we said CPU is executing the program. So now my question is this: is operating system running right now? No, right? Operating system is not running right now because there is only one CPU and it's running the program code. It's not running the operating system code. But operating system is there in the memory, right? Operating system is there in the memory. So it is ready to be executed. It is basically in ready mode or ready state, right? If this program calls, makes some system call, operating system can immediately run because it's there in the memory, right? Right. So it's in some sense, it's in the ready state. So that's what we mean by operating system is running all the time. So whenever the statement is a little bit broad, when they say running all the time, it basically means that you can call it anytime the application program calls some, makes some system call, operating system will be there in the memory. That's what it means. Okay. So these are somewhat broader statements. You have to take it with pinch of salt. So it is always there in the memory, but it need not be running all the time. Because in this case, clearly you are running some other program while operating system code is sitting idle in the memory. I hope that makes it clear. Right. So running all the time is a bit of a broad notion. So the question is this: during execution of user programs, program counter still needs to be updated, right to fetch next instruction. Correct. So after every fetch decode execute cycle, program is counter it gets incremented by 1 in hardware. This happens in hardware. It automatically gets incremented. So as we have discussed, program counter will change the mode bit. So shouldn't so the mode bit for changing the program counter in very specific cases, right? So changing the program counter in a very specific cases will require OS support. So the case that we discussed last time was the case of, it was the case of running a new program. So, and we saw that when we are saying that we want to run a new program, it means there are some old program which was already running and now we want to run a new program, and this basically has between program operations, between programs operations. So this is between program operations. In this case, you have operating system has to change the program counter in some way that it wants, right? Here you are doing critical operations. And that's why you need mode bit to be 0. In other cases, for example, like executing your regular program, right? Executing user program. Updating program counter does not mean or does not have any consequences, right? Does not affect other programs. So no OS support is required. Right. So in this case, this can happen in mode equal to 1. Right. So you always, whenever you see some operation, you always ask this question: is this operation affecting the entire system, or is it local to that particular program? So for example, calling a function is local to that program, but running a new program itself is kind of like affects other program also, right? Because operating system has to get involved in this, right? So here it's a critical operation. Changing the program counter in this case is a critical operation. That's why its mode is equal to 0. And again, this here its mode is equal to 1, right? I hope that clears the doubt. So question is this: how system call works we know, but what exactly it is it the word that connects user to operating system to perform critical operation? Yeah, correct. It's kind of like correct. It's kind of like a function that is provided by operating system to achieve certain tasks, right? And there is only specific way of calling this function, which is through the trap or the software interrupts, where you have this bit operations happening, like bit is set to 0 and all. Is that okay? It's in some sense it's a function call, but it's a very, very special function call where you have this protection and bit operations and all. That's it. Okay. Let's get forward now. Yeah, so basically like it's basically something that we did not discuss in last class, but we'll cover this time. So how exactly the system starts, right? When you press the power button, what are the different operations that happen so that your system actually starts and you get this what UI or something like that, right? Like you see Windows screen or you see junk screen or whatnot, right? So how exactly does that happen, right? So we'll get into that. So when you press the power button, let's say when you say the power button, yeah, I should change the color. So when you press the power button, right, it basically sends a reset signal to CPU. So remember that your CPU is exactly a hardware chip, right? It's a hardware component. It's a chip. It has a reset pin. So it literally is a wire. There is a reset wire. So I don't know what about the recent computer architecture, but in legacy systems or like the old CPUs used to have this reset pin, right? So whenever you press the power button, there is somewhat like a signal which goes on to this reset pin. It's kind of like an reset interrupt, something like that, right? So whenever CPU gets the reset signal, whenever CPU gets a reset signal, it starts executing code from a fixed memory location. So you press a reset signal, there is a fixed memory location, and this is again fixed memory location fixed in hardware. Again, this is the entire thing is in hardware. It throws whatever it was doing, it throws everything out, and it will directly start executing whatever is there at this particular fixed location. This fixed location is generally, what do you mean by signal? When it basically means that you press a button, right? When you power your system on, you press a button. That so that button basically sends a interrupt kind of signal to the hardware. It's a electrical signal. It's yeah. So then it starts running from the fixed memory location, and fixed memory location is something called as ROM or read-only memory. Okay, and it has some fixed code there. So that code is called as bootstrap or bootloader. Again, this is a fixed program. Somebody has written it and somebody has saved it into this read-only memory, and it's always there. So whenever you press a button, the reset signal will go to CPU, and CPU will automatically start running whatever code is there in this ROM system. This ROM basically there is another chip, there's a memory chip, and whatever this code has been there, it will start running that. Is it understood at this point? That location is what? Point by the register. Yeah, that location is fixed. That location is fixed by the hardware. So what it basically do is like whenever you press the power button, that location will be loaded into program counter, and it will start fetch decode execute from this particular memory location. That's it. So whenever I say executing, it means basically it will set the program counter to this address of this fixed memory, and then it will start executing whatever code has been there. Any doubt in that? So question is, so booting means starting up. So here in the question itself, they have mentioned it. So booting means powering up. Yeah. How does the system start, right? How does the operating system loads, right? That is the question. So I guess up to this point, it's okay, right? Yeah. Okay. So now currently just remember in back of your mind that currently the bootstrap is running. The bootstrap program is getting executed at this moment, right? So now your operating system code. So I'm saying operating system code is on the hard drive, right? Your operating system is on the hard drive because it has to be stored in some permanent storage, right? Which is your hard drive. It's not in the RAM as it yet. Currently, not in the RAM. So your operating system is currently not in the RAM because you have pressed the power button, right? The system was off before this. You press the power button, it means your entire RAM is basically empty. It has nothing going on there, and your CPU is executing this bootstrap program, and operating system is not there in your RAM, right? But operating system code is present in hard drive, right? Is this understood? Okay. So now let's understand this hard drive in a very superficial manner. So your hard drive is again basically a memory only. It's a storage memory, but it's quite slow. It's again some kind of a storage, and it itself has some addresses, right? 0, 1, 2, 3, and so on and so forth, right? So it's basically similar to RAM, and it has its own addressing, some one way or the other, right? We don't care what that addressing is, but there is basically 0, 1, 2, 3, and so forth. Something like this is also there in your hard drive also, right? Is this understood? Basically, it's similar to your RAM only, and it has its own addressing. What that addressing is, we'll see in file system. At this moment, we don't care. So again, here at this particular fixed address, generally the first address, why slow? Because it's far away from your CPU, right? It's away from your CPU, and it generally it used to be magnetic. So there used to be these cylinders and all that, right? So it's hardware problem. Yeah. So it's not software issue, it's a hardware issue. Right now it's much faster because of this SSD, and but yeah, whatever, right? But it is just slower than RAM in any case. Anyway, so in this first location in this secondary storage or hard drive, it is also called as block. In the first block, it has what we called as the operating system starter code. So in this particular section, there is a code which basically loads the operating system. So if the CPU executes this particular code, which is stored in the first block of the hard drive, then it will be able to load the operating system, right? Now who writes this code? Operating system. Whenever you install an operating system, that installer of the operating system writes this code. Or maybe I should write it here. This code it's basically saved when you install operating system. So now nowadays it directly comes with your laptop only. So you don't have to worry about it who writes it, but it generally whenever you install an operating system, it basically gets it, right? Okay, so the question is, hard disk has infinite memory? No, it does not, right? You have hard drive 1 TB, 2 TB, something like that, right? So it does not have infinite memory. That would have been nice, but yeah, it does not. Anyway, so up to this point is okay, right? Okay, so now what happens is basically this. Now the bootstrap, remember that we have started running bootstrap, right? Bootstrap copies this particular code, copies this particular rows, this code into RAM, into main memory. Okay. Correct. So at this point, up to this point, only bootstrap is running. OS code is not at all running. Okay. OS code is not at all running. Only bootstrap is running. Then now this code, right? This code knows how to load the operating system into the memory. So this particular code, it knows how to start the operating system. Right. And again, this knows because whoever has developed the operating system has written this code. So they know how to start the operating system, right? So what bootstrap will do, it will load this part into the memory and start executing this code. Is this understood? Yeah, and once, and basically this code, once above code execution completes, operating system starts running. Okay, that's it. So once this code this code completion of running this code completes, so your operating system starts running. If there is a OS, then it is the first block. If we have more than one OS, how it selects. So in this case, if you have more than one block, there is a second bootloader, or there is a second bootstrap program which is resides in this place. If you have more than one operating systems. So here what we said is like this program basically loads operating system. So if you have multiple operating system, this program itself will be much more complex for more than one operating system. Yeah. So bootstrap program loads whatever is written here in this particular region. Whatever is there, bootstrap only loads that. Bootstrap doesn't know that whether it's operating system or whatever, right? It loads that. It can be another bootstrap also, in case you have multiple operating systems, right? Then you can select and all that, right? So it will display and whatnot, right? Yeah, correct. But if you have any single operating system, generally it is okay to assume that this is some OS loading code and it will basically run that. Yeah. So you can just say normal OS, right? So this code is also part of your operating system itself, but this is just a loading code, but your normal OS operation starts once this code finishes, right? Okay. Yeah, sleep, sleep is a different case, right? Like we won't discuss that here. This is not for sleep. Yeah. This is when you start your computer. That's it. Correct, correct. So question is basically this: bootstrap load whenever written, whatever written in the 0th memory location. Now the loaded code which was written in 0th memory location knows how to start an operating system. Yeah, that is correct. Where the bootstrap is loaded, it's there in the ROM. It's loaded in, it's there in the ROM, right? It's already there in the ROM. It basically, and it is this reset signal is basically always points to this ROM location, and whenever you press it, it starts executing from here. Right. Again, this again you will have to move into RAM and all that. That happens internally, and those are very low level details. Is this understood? Okay. Now there is one crucial part. If you see here, in this bootstrap code itself, or whenever we are loading the operating system, we are interacting with hardware, right? So while loading the operating system, so bootstrap is interacting with hardware, right? Which basically implies that it's running critical code, right? It's running critical code, right? It basically means that the mode has to be 0, or basically in kernel mode, right? So whenever you press the power button and your system starts and the CPU gets this reset signal, by default it starts in kernel mode, because all these operations require this IO operations and all, right? So it generally starts in kernel mode only. Once the operating system load is finished, then only the operating system will itself turn it back to user mode after this. Is this understood? So by default, when you start your system, it will start in kernel mode, because it has to perform this bootstrap, and all other programs have to perform this IO operations, which are critical operations. So they have to be done in mode 0. Sir, is it fixed? It will start from 0 location only? It need not to be 0, but some fixed location. So question is that is it fixed? Is it fixed? It will start from 0th location on reset. It need not to be 0th location, but it is a fixed location. something which is kind of like constant for that particular system. So Bootstrap is actually a low level setting, correct? So it is a low level program. I don't understand this question. Nobody is used to interpret the process. So there is no process up to this point, right? Only thing that we have is like loading of operating system. That's it. So once the operating system loads, then only user comes in. User cannot use the system before the operating system is running, right? Or before it is loading. Yeah, you can try interrupting system during this load also, it will crash. You can try interrupting your system, it will crash and it will again perform a reset generally. So during loading, you can of course interrupt system execution, right? You can press some button and all that, right? Then again the system will crash and it generally restarts. Generally it restarts. So for example, in most of the system, while if it's restarting, if you press Control Alt Delete, it restarts. Don't try that. If your system goes down, I am not responsible. But yeah, you can do that because it's your system finally, right? So you can do that, but it comes with risk. Right? Your system might crash. There can be some issues with later on, right? So don't try that. But yeah, nobody's stopping you from doing that. Yeah. Yeah. So again, yeah, this is basically in the summary of what we just discussed. Right. Any doubt in this? Okay. Okay, let's move forward. Okay, now we'll look into how exactly a program runs on a machine. Okay. So first step of that is user writes a program, right? So here you write some kind of a program. We'll see the addition case, right? We'll write a program to add two numbers, right? User writes a program. Then you use something like a compiler. Again, this is just a generic term. Like you can use interpreter, whatnot. Right? 1,000 things are there right now, but assume that you are using a compiler. The compiler will convert your user written program into something known as executable code. Right. So this is some kind of a, you can say, machine language. That CPU understands. So you write a program in your language, right? For example, C, C++, Java, Python, whatever, right? That is user level language. So you understand that language, but CPU does not understand that language. So you have to convert it into something that CPU can understand. So there are some programs called a compiler. Anyway, you get to know this in the compiler thing, right? Whatever, right? Compiler model. It will convert it into some code which is understood by the CPU, right? It is called as executable code or executable file or a byte code, something like that, right? Once that is ready, so for example, if you have ever run the C programs, right? So what you do is basically gcc code.c. This is the command that you run and it generates ./a.out, right? Have you guys seen this file? A.out file? Yeah, so A.out file is basically your executable code or byte code. Executable code for your this code.c program. Yeah. Okay. Then so this file is basically executable, right? And when you run this particular command, you run this particular command to run your code, right? You basically, what you do is basically you request the operating system to run this particular byte code or executable file, right? So whenever you do gcc code.c, it generates A.out file, and when you say ./a.out, you basically request operating system to run this particular code. Is this understood? I write a program means, wait, there was a question. I write a program means it is in main memory, right? Then OS loads the program into memory. No, you write a program is a very different stage. You can write it on your paper also, right? And then you store it in your hard drive. We don't care how it is written. We just hope that it is written. How it is written is you might use some editor or whatnot, right? That is not our concern at this point. We don't care. We just hope that it is written and it is stored in the hard drive. Writes a program, and it basically means that it is stored in hard drive. How it got there, who has written it, how it is written, we don't care. At this moment, we don't care. Okay. Only thing is that then you run some other program, which is a compiler, which will convert your program into this bytecode, and then you request operating system to run this bytecode, which is ./a. Right. I hope this is understood. Okay, great. Then operating system loads this program into memory, whatever that means. We'll get into that. Get into this in a little bit more detail in next slides only. It basically loads into the memory. So currently this file is on hard drive. This executable is on hard drive. When you say, when you request operating system to run the bytecode, operating system will start loading it into the memory. So operating system will move this. This is your loader. So it's a piece of code in operating system which basically loads this executable file from hard drive into the main memory, into your RAM. Okay, we'll get into that, how exactly it does it. But there is some piece of code in operating system. It's called a loader code. It will basically take the executable bytecode from your hard drive into the RAM. Right. And then operating system will set the registers properly. So for example, it will set this program counter and all that accordingly based on where it is loaded into the RAM, and then it will start running the code. Is this high level picture clear? Shall we move forward? Okay. Well, now let's see an example which will give us some more insights, right? Oh my God, wait. Yeah. So I'll readjust it later. So consider this is the program that you have written, right? So first thing that we understood is like how the bytecode looks like. How exactly this bytecode looks like. That is the first thing that I will try to understand. Again, I will not go into very deep details. Just superficially, I will explain, right? So it generally, when you compile this code, it generally, the bytecode has two sections. Again, this is a very broad statement and you have to take it with a pinch of salt. There can be more sections also, but generally there are two sections. One section is data section. Another section is code section or text section. Text or code, whatever, right? Okay. It generally has two sections, right? This bytecode. So compiler will create these sections for you. So in data sections, you have your global variables and whatnot, right? Global variables and other kinds of stuff, right? This data and all that, whatever you have it in data section. And here you actually have your code. So code in the sense like whatever is the compiled version of this code, right? Your functions and your actual running actual code, right? Again, it's called code section, so it's kind of opposite, right? There can be other sections also, but we don't care at this point, right? This is what we require to understand the example. So who creates these things? This is the structure of your bytecode file or a.out file created by compiler. So your compiler takes this program as input and it creates this kind of structure, right? That's it. Is this understood? Okay, great. So we are at this stage now. So this is, we assume that this is written by some guy somewhere and it's already there. Then you compiler converts it into bytecode. Now you ask operating system. Now we'll go to the next stage. So the third, again, this is 1,2, right? Like whatever. So Yeah, we don't care, right? Like it can be stored, depends on how the compiler works, right? Local variables are generally stored on something else. We don't care at this point. We'll get to that in some time. Only thing is that there are some sections, right? Some these sections are like there. That is the point right now. It has some structure and compiler sets it properly, right? Okay. Local variables, and we'll get to that in after some time, right? That is not a valid concern at this point. So the third step was that user requests operating system to execute the code. How will it do it? How can user request operating system to execute some code or execute some program? Correct. Software interrupt, but we have a name for it now, right? Yeah, software interrupt trap, but we have a better name for it. Those are correct answer, but we have a better name for it. It's called system call, right? Syscall, correct. So there is some system call. No, don't get into context switcher at this point. We'll discuss that later. So we are not at that point. We are not ready for context switcher. So answer to this question is like this happens to some system call. Okay, it happens to some system call. So the user says that this is my bytecode, or this is my executable code, a.out, and ask operating system to run this code via some system call, right? Is this okay? Okay, now let's get to step 4. Operating system receives the system call. So which system call? System call is to execute the code. This is the system call that it receives. Okay, it receives the system call, and so it knows the system call is execute code, and it knows that this is the executable file, and starts running a program called as loader. So, loader program or loader code, whatever, right? So there is a special, you can say, a function in operating system which is called as a loader function. Is this understood? Now let's move forward. So maybe use this one only. Okay. Now 4.1 loader copies the bytecode from hard drive to some memory. So there was third point. So what is the doubt in third point? So the thing is that whenever user wants to run some program, it has to request operating system saying that, okay, I want to run this, right? That is the design that we have been following, right? So to anything, any request that user makes has to go through OS through this system call, because we want to have that mode thing, right? We have to change the mode. So only way we allow user to ask operating system anything is through the system call only, so that this mode change can happen, right? So there is a system call to run this particular code. Which system call is that? We'll get to that later on. Okay. Is this understood? So now when the operating system receives this particular system call to execute some code, it runs a program or code called as loader code, which is there in operating system itself. And the loader, the first task that loader does is it copies the bytecode into the memory. Now which memory? Operating system will figure it out. Operating system knows. It's an because this is again resource management, right? Whenever we get into some memory, it's resource management. So at this point, we will assume that operating system knows where to do it, right? Great. Now this guy, loader, whenever it's copying, right? Like whenever it is copying, it copies appropriately in the sense that loader copies dot text and dot data into in some memory layout instead of saying some. So don't worry about this point. I'll explain it in some next slide only. Okay. So the only thing is that whenever the loader tries to copy this thing from the hard drive to the memory, it it copies data into some section and copies text into some other section. So this is the memory which is allocated for your program. This is the memory which is allocated to your program or allocating for your running your bytecode. So again, this text will go into some part of this memory. So for example, somewhere here, this data will go somewhere here. Something like this will happen. So how exactly, how exactly this structure looks like, so we will see it in like sometime. But operating system knows what exactly is this memory layout of the process, and it will just copy it accordingly. Any doubt in this? If you don't understand this right now, we'll explain it in some time anyway. Okay. So once this entire setup is done, then operating system schedules the program for execution. So why byte? The question is that why does bytecode have different sections? It is again somewhat as a design choice, right? If you allow bytecode to be written in whatever way you want, so basically this is a compiler. This comes under the compiler's domain, right? If you don't enforce any structure into bytecode, then the compiler can write anywhere whatever it wants, right? Then loader will not know how to basically form this memory layout. What is the predefined structure? We'll get into some point. There's just wait for 2-3 slides. We'll get into that. Right. Okay. So if you don't have any of these structures, it means the loader program itself doesn't know how exactly this program looks like. So for example, when we say operating system starts running the code, right? So it should know where is the entry point. You understand the issue, right? So in this case, whenever we ask operating system to run this particular code, the operating system should know where the main starts, right? Isn't that right? So then when loader is loading this particular executable file, the loader should know the starting point or the main, right? Isn't that right? Do you guys agree with this? Yeah. So for knowing this, you have to enforce some kind of a structure on this. Just to do this basic operation, knowing this entry point, there has to be some structure to this bytecode, right? Is that understood? Yeah. So the compiler follows that structure. Whatever you generate out of compiler, it will basically follow that structure. That is for sure. Right. Is this understood? this is why execution starts from. This is something that has been decided between the operating system and the compiler, right? So operating system expects some information in this bytecode which tells that this is the starting point. There is a way in this bytecode which tells the loader program that this is the entry point of the code. The compiler says that whatever is written in main, it will be posted into that location. So it's basically something like this. So operating system expects execution starts from main program. So main program or some predefined label, right? Main is just a label, main location. And compiler ensures that whatever you have written in main is properly placed into that particular location. So this is main function. Okay, so this is what it is, right? So again, this is not very interesting from operating system perspective. This is something that you will get to know when you look into activation records and all, right? So from operating system perspective, there is this is not so interesting. Only thing is that there is a structure to this bytecode. That is the whole point, right? There is a structure to this bytecode. That is exactly our point. And this structure has been decided by the operating system, and compiler follows that structure. So if the file does not follow the structure, the file will not run. The program will not run. The executable will not run if this structure is not followed. Is this understood? I don't know where it is, right? Like I don't know. But this is not part of this particular topic. That's all my fault. Activation record, where it is, I don't know. Okay. But you understand this, right? The operating system expects that this bytecode is in some particular format, right? Is this understood? Okay. So now I'll just write a comment, but like, yeah, I won't entertain any question answer. This is why Windows.exe files do not run on Linux. Yeah. Okay. So this is the reason why Windows.exe files do not run on Linux, because they expect different structures, right? That's it. This is one of the reasons. If you have any doubts in that, I'll suggest you have some additional readings. Right? It is not very interesting for the current topic, so I'll just leave it there. Okay. Any doubt up to this point except for this particular thing? Okay, great. So we have written here that it says schedules a program. So basically, we'll explain this in a little bit more detail later on. So let's move forward for now, right? So note that when it loads the program into the memory, it becomes a process. So now we will understand what a process means, right? So here, after this stage, maybe I should use different color. At this particular stage, program becomes a process. Again, this is a very subjective definition. I'll get to that later. But like, I just want to coin this term here. So once the operating system schedules something for execution, it becomes a process. Okay. Some might say it becomes a process at this stage itself, even before it is getting scheduled. But yeah, sure. What not? Depends on the design of operating system. Okay. So now let's understand what exactly we mean by a process. So if you see most of the books and all, they say informally a process is program in execution. So Again, when you say program, it's basically byte code. Whenever your byte code is in execution, it means it's running, then we call it a process. That's a very informal discussion. Again, it is a very broad way of explaining what a process is, but there are many different cases where we have to disagree with this, right? Again, it's not, I'm not saying it's incorrect. It's a very broad level of statement. That's it. Again, we don't know what do we mean by in execution, right? It might mean that CPU is running, it just might mean that it's in the memory, right? So it's the similar thing that we had, right? Operating system is always running. It's not neither true, it's neither false. It just makes sense under some separate context. That's so it's again, this definition is like that only, right? So in our case, what we can say for sure is, right, it's a process if it contests for resources, right? So what do we mean by contest? So we have CPU, right? And we have RAM, and we again have IO, whatever, right? So multiple resources are there, and a process is a program which contests for all these three resources. It basically wants CPU to run, it wants RAM for its execution. It might want IO also, right? It might want IO also. So if a program demands these three or more than three, whatever our resources are there, demands resources, so it demands resources, any of these resources are more than these resources for execution, for running, then we can call it a process. That is also one way of describing it. Okay. Is there any doubt in this? Okay, now we go back to our example. At this particular point, right? At this particular point, the process already has some memory, right? It has been loaded. So it has some memory here, right? Since it's all loaded, it has some memory and it is scheduled for execution. It means it's asking for CPU. So we say this is a process. Okay. So I think context of a process, I'll describe it in some later slides. And it is just a term that I wanted to coin. Maybe, okay, so I'll give you some vague idea about what do you mean by context of a process. So consider that. So again, this is not the complete thing. What do you mean by context of a process? It's just some vague idea that I want to give you before we proceed, right? Okay. When so we consider the case when a process is running on the CPU. So it is currently the code that CPU is executing is for that particular process, right? It can be our addition program or whatnot, right? So CPU has registers, right? CPU has registers. So these registers contain values or data. Maybe data is the appropriate term. Contains okay, data specific to the process. So because currently the CPU is executing that process, right? So whatever values are there in the register, CPU's register, are basically specific to the process, right? Okay. Similarly, there are other components in the hardware also. So for example, there are memory management details, right? Again, we won't go into details. So basically, this means or very superficially, where in the RAM is the running process. So this information is also there. So whenever its process is running, the CPU should know where in the RAM, basically like exactly in the physical thing, where is this process residing, right? Because it has to fetch the data from that, fetch the code from that, and execute. So this information is also there. Is this understood? Okay. So additionally, there are other things also. So for example, file system we have not covered, but the process may have additional files, right? The process may use some files, right? So we again, we need to keep track of that. Those. So currently running process, it might be using some file, right? So what are those files? We need to keep track of those also, right? Okay. So it might have additional some hardware also, right? Hardware, what we can say, requirements also, right? So all these things are there, right? So you guys understood these 4 points, right? Okay, so let's go forward. So these things form the context of the process. So again, this is not an inclusive definition. There are additional components also, but this is just to give you an idea. That's it. So whenever we say context of the process, we talk about what exactly is in the memory of that process, what exactly is in the registers of that process, of the CPU who is executing that process, what exactly are the files that are getting used by that process, or any other resources that the process might be using. We talk about that, and that what we briefly call as context of a process. Is this understood? Okay. So now we look into the memory structure, right, that we talked about, right? This is the final part. When loader copies the bytecode of a program from hard drive, it copies it in following way. Okay, so remember that on your hard drive you have this executable file a.out, and it has some specific structure, right? Dot text is there, dot data is there, right? So whatever, right? In order might be different in the example that you saw, but whatever, right? Maybe just use that one just to avoid confusion. And data, and there is text, and there can be other sections also, what, right? So and whenever we ask operating system to run some program, right, it assigns some memory in your RAM where it can actually copy, right? So loader has to copy this particular file from the hard drive to RAM, right? Some portion of the RAM, there is some region in the RAM where the program should go, right? So it generally copies it in something like this. So this is the portion of the RAM where the program should be, and loader will copy it in something like this. So that this text will be copied here, right? Again, then there is this data. Data will be copied here, right? Something like this is there. Then there are additional two sections. One of them is called as stack. So note that up to this point, the process is not running. It's not in the running state. Okay. It is just loader is just copying it into the RAM. Right. And there is heap. Okay. So it copies it into this format, right? So now here your data has global variables or global variables, or okay, fine. And this is your code. So somebody asked like, where are the local variables, right? So local variables only make sense once your program starts executing, right? So you have written int a equal to 1 in your main code, main function, right? So unless and until main itself runs, you don't know what is the value of a, right? Is this understood? So local data will eventually come in when the program actually starts running, right? So you know it's one because you have written it, but actually system will get to know that once it starts executing, right? That it will only happen that way. So that local variables will be stored in stack. And this will become active once the program starts running. The stack will become active when the program starts running. Again, that activation record thing will gets into picture here only. Activation record and all. They are part of the stack itself, right? Any doubt in text data and stack? So there was a question. It is, if it is stored in global, sir, right? If it is stored in global, then it will come in this data section. It comes in this data section, right? If it's local, then it local variables go into stack, something like that. Is this understood? Okay, if you have any doubt, you can ask. So only thing is that there is another, so we can write as this. A process can request more memory from operating system, and that memory will be given to the process from this heap. Okay, how exactly this expansion happens, we'll see it in memory management. Okay, is this understood? So there was a question, is this structure is specific to the particular code? It is general for all kind of code. This structure is general for all processes. This particular structure is general for all processes. Non-stack part here has any name? Static memory? No. Non-stack part is basically this thing is empty. This is currently empty, and we can increase or decreases as per the program state. Okay. For example, you can program can ask more memory to the operating system through malloc or embark system call, whatever. Right? Correct. Malloc and all, right? So that's. So again, this also comes under for which we are using it. So for malloc, whatever memory that you get from operating system from malloc, we will be using heap for that. So now, so this also comes under process context. So where is my stack? Where is my heap? What kind of things has been allocated in heap? Again, where is my data section? Where is my text section? All these things again come under process context. Is this understood? Yeah, it can be indexed. We don't care how exactly it is stored, but this information is stored in, needs to be considered in some manner. Right? It is an index number, whatever. We don't care at this. So in broadly speaking, if you look into a process, this is what it will be looking. This is how it should look like. when it's in the RAM, when it's about to execute or when it is executing, this is how the process will look like. There will be some part of the code, some continuous part of the code. There at the end there will be text. After that there will be data. Then there will be heap and there will be stack. And this can be increased and this can also be increased as per the need. Okay. This is how we view the process in execution. This is a view of the process in execution. Okay, is this understood? Keep this in back of your mind. It will go crazy when you go to memory management, right? So at this point, just assume that this is some portion of the RAM, which is some continuous portion of the RAM. What should be the size of this portion and all that, we don't care at this moment. We'll get to that in memory management. It basically, a view of our process in the RAM is basically like this. If we ask how is my process doing in the RAM, this is how it is doing. This is how it is stored in your RAM. This is how it is stored in your hard drive. But once you ask operating system to load it, this is how it will be looking into your RAM. Is this clear? At this moment, assume that it's contiguous location. At this moment, assume that it's fine. Don't add unnecessary complexity at this point. Assume that it's contiguous, right? We'll understand these problems when we actually go to memory management. But at this point, just for sake of understanding the concept of the process, you can assume it to be contiguous. Okay. Fine. So all these things we need to keep track of. As an operating system needs to know all these things about the process. So for example, where is for example, this is the thing, right? This is somewhere in the RAM. So where exactly it is in the RAM, it has to know. Again, in that particular location, where exactly are this stack, heap, data, and text, it has to know, right? Again, all these things it has to know, right? What are the registers that are currently being used and whatnot and all that, right? What are the hardware requirements? What are the files it is using and all those things, right? It has to know, right? So this is all this information, all okay. All this information is needed by the operating system as it concerns resources. So see that all this information are concerned with resources, right? Like where is my memory, how exactly it getting used, what are the files, when you say it's basically hard drive, how are they getting used, what are the things on CPU, how are they getting utilized. All these things are required by the operating system because operating system will manage the resources, and since process currently is using these resources, it should know. All right, okay, is this point understood? So it's operating system's job to keep track of this entire context. Is this understood? There was a question. That means there will be multiple stack in RAM based on number of processes. Yeah, correct. If you have multiple processes, there will be multiple stacks in RAM. Okay, so now since operating system need to keep this information somewhere, it has a specific structure for it. So the operating system has a special. Now this is literally a C structure. Okay. It's literally some C structure. Again, and C is a general language for writing operating system. That's why it's a C structure. It's not very kind of like special about it, but operating system has a special structure for it, which is called as PCB. It's called as process control block. So all this information that we discuss, operating system will store this information about all the processes into some structure, right? So yeah, OS doesn't itself does not have a structure. It does have a structure. It's a very separate. It's a very different and separate structure. How it is exactly handled, that is depends on the design of the operating system. It might be through PCB. It may not be through PCB. Depends on the operating system design. Okay, but it does have its own very special structure. It does have that. Again, that is not very interesting to us. So because we are more interested in processes. So now this thing is literally a struct. So if you go to Linux, it's called task struct, task underscore struct. Windows, I don't know, but in Linux, it's called task struct, right? It's literally a C code. It has all this information. What is the process state? We'll get to that. What is the process? So the one concept that we need to know is like process number. So every process has a number. Okay. Again, this is a part of a C structure. This entire thing that we have drawn is part of a C structure, right? So it means it will have a data type. Is this understood? It's basically this only. There is some structure and there is some unsigned int 32 or whatever, right? 32 underscore C PID, process ID, or process number, whatever, right? So it has some type, right? Is that understood? It can be a 30 integer of size 32 bit or 64 bit or whatever, right? Okay, so it means the process number can go from 0 to some maximum value, 2 raised to 32 minus 1, if it's a 32 bit integer. Is this understood? Every process has a number, and for storing that number, there is a field in the structure in the PCB, right? And that field has a data type. It can be 32 bit or 64 bit or something like that, right? Integer. So there is a basically a range of process IDs from 0 to this particular thing, 2 raised to 32 minus 1. Okay. And basically this means your number of processes cannot be more than 2 raised to 32 if it's a 32 bit integer, right? Because you can assign numbers to only 2 raised to 32 processes, so you cannot have more than that processes. So if you want more processes, you have to kill some processes and use their PID for the new processes, right? This is basically this. What I wanted to say is that you can only have finite number of processes in your computer or in your operating system. And if that's not a drawback, because this number itself is quite high. This is very high number. This is greater than million. So you don't have to worry about it. Is this understood? Yeah. So again, like we said, right, we have to keep track of all entire process context. That includes program counter. We already discussed this. Again, registers, right? Whatever is currently in CPU register for a running process, we have to keep track of that, right? This memory limits is basically again this particular part where exactly in the RAM it is there and where it is this and all that, right? And then finally you have open file list of files, again the files that it is doing and some other stuff. Okay. So there are a few questions. Let me see. Difference between context and PCB. PCB is a special structure by OS for storing the process info, and the context is a process info in RAM. So don't look at it like a difference between those two, right? So context is basically a concept. It's just a concept. So it does not really exist in operating system, right? When we say context, it basically means that we are talking about this process and this is the details of that process. It's a concept thing, right? PCB is something that is actually presenting in your RAM. Again, it's not like you should be comparing these two. It's like comparing apples and oranges. It basically just context is just some concept that we'll be using in some next slides. While PCB is something that is operating system uses to keep track of all this information. Where does PCB stays, right? Like, yeah, we'll get to that. So now you have multiple processes, right? Let's say you have, assume we have 3 processes. Again, when I'm saying processes now, it means they are there in the memory. They have all this information for them, right? All the 3 processes will have all this information from them, right? It basically means that there are 3 PCBs. So there are 3 process control blocks, one for each process. Okay. Operating system stores them into somewhere in the RAM. So operating system stores them somewhere in the RAM. So assume that this is your memory. This is your hardware memory. Okay, complete RAM. All RAM, right? So some portion of this RAM is generally reserved for operating system use. Some portion of this RAM is generally reserved for operating system use. An operating system can choose whichever way it wants to use this particular memory. So no process will be using this memory. Only operating system can use this memory, and this is reserved. So it completely belongs to the operating system. And in this reserved section, it stores the PCB. So all this PCB will be stored somewhere in this reserved section. Right? Is this understood? Okay. So now, generally, operating system maintains a linked list of PCB. So we have 3 PCBs, right? So it will be something like that. PCB1, let's call it, okay, maybe let's call it PCB1. It will have this entire thing, and there will be forward and backward pointers. So there will be a forward pointer to the next PCB. PCB2, again, there will be a backward pointer here. Again, something like this. So this is basically a linked list. Okay. So now let's say 4th process comes in. For whenever the 4th process comes in, operating system creates a new PCB. How does it create that? We'll get to that. It creates a new PCB and it basically adds it to the list. Singly doubly, that depends on operating system designer. It need not to be a list also. I'm saying generally it is a list. It can be a big array also. It can be an array of size 2 raised to 32 minus 2 raised to 32, right? It can be that also. It's the operating system designer's choice, right? Generally, the most memory efficient way is basically using a linked list. So most of the system generally use that. But again, this is not a hard rule, right? You should be only using linked list. You can use any data structure you want. Somebody can use hash table also, right? Doesn't matter. May not be a good operating system, but whatever, right? Works. And whenever some process terminates, right, the operating system will delete this PCB from there, right, once the execution completes. Any doubt in this? There was one question. So when process is removed from the RAM, its PCB is moved to hard drive. No, it is deleted. So when you say removed, I am assuming it means the process terminates. The execution is complete. In that case, it will be deleted. The PCB will be deleted. and the memory will be free. Okay. So everybody understand what a process is now? So process is some program which is in your system. It's there in RAM and it is contexting for your CPU and other resources. It has its own context. And when we say context, it's basically whatever data related to the process is there in the CPU registers and all that, whatever the files that are getting correctly executed and all those things, right? All those things. Again, that is, we'll explain that in a bit detail when you look into context switches. But generally, the most important part of a context is basically the CPU things, CPU registers and all. This is the most important part, right? Again, this includes this memory, this memory information as well, because all of these things will also be present in some CPU registers anyway. And then, oops. Yeah. And then basically we saw what is a process control block. It basically keeps all the information regarding some process has to be kept there, right? How memory is deleted? Memory is deleted is like, it's not deleted in that sense, it's basically freed, right? So it's basically a linked list, right? It's a linked list. You just remove this node, that's it. So you whatever implementation you saw for linked list in C, right? There is some similar equivalent in operating system. That's all. Yeah, it's basically free. Yes. How does that work? We don't care at this point. And that, I don't think that is there in this entire setup anywhere. It's a very low level detail. So there are different algorithms for that itself, the buddy system and all that, but I don't think that we need to cover anyway at this point. For now, just assume it will be freed somehow. Operating system knows how to do that. Okay. Is this okay? Okay, now, so we saw that whenever when we wanted to create a new process, right? The user asked operating system to create it via a system call, right? User asked operating system to create it via a system call. So that system call is a fork system call. Again, this is in Linux or Unix, whatever. There is some, okay, Windows has a separate system. We will discuss that maybe later. But in Linux, it's basically there is a system call which creates a new process, right? That's it, right? It creates a new process. It's called a fork system call, right? So let's understand how exactly it works. So when you, what would be the best way to do it? Okay. Fine. Okay, so when you run this a.out, right? When you run this command on your command line, you run it on your, generally it's called a bash shell. Or maybe you, or sometimes what you do is like click on something, right? Click on a program or bytecode so that it runs. So you have some interface where you click something or you type something in, and the operating system knows that you want to run something, right? All those programs are generally called as shell programs because they provide you some kind of an interface to interact with the system itself, right? It can be bash shell or it can be something like your UI or something like that, right? Whenever you do this a.out, you basically tell this particular program, you tell bash, or maybe I should just say shell, that you want to run ./a.out. Okay, let's understand it in a little bit more detailed manner, right? So here is your operating system, right? Here you have your code a.out, and you want to tell your operating system that you want to run this a.out, right? So either you can So there are one option, either you can initiate a system call yourself, and then operating system will start running to that. But there is a more convenient way is there. So there is a more convenient way is there. Is to have an UI. So for example, if you want to play a song, it's very inconvenient that you have to type some system call every time, right? You just wanted to play a song, would you go and type an initiator system call? That's very painful, right? So what generally there is another component in between, which is basically a UI component, right? Your user interface, whatever you see on your screen, whatever, right? Or it's a command line interface like bash, right? You basically, what happens is like, instead of directly telling operating system, you tell this particular UI. How do you tell it? You by click on that program, that's it. Or you type that program's name, that's it, right? You tell this intermediate UI that you want to run this a dot out, and that UI itself will then make the system call. So it's basically somewhat similar to what we had for the library thing, right? You don't directly call the write system call, you basically do it through some library, right? It's basically the same thing. Instead of directly writing some very critical, like very complex system call, you instead do some kind of easy actions, and this UI guy will take care of everything else. Is this understood? This is understood, right? Okay, great. So now what we want to understand is what exactly happens at this particular point. This is our point of interest, right? So you yourself had told this intermediate guy that you want to run this program, but that is not very interesting. What is interesting, right? What is happening in between this, right? Okay. I hope this is clear. Okay. So in general, whenever we want to run a program, it is done in two steps. First step is create a new process. And second step is load the program into the new process. I'll explain this. Okay, so when we were discussing how exactly the program loads, right, we saw that there is this loader code which basically takes everything from the hard drive and do that, right? And there we actually did not discuss some point. For example, where did that go, man? We did not discuss this point, right? We said that there is some memory, right? So some memory, we said it copies into some memory, but what memory we did not discuss, right? We just said that OS knows that, right? So before even you start copying, the loader can start copying something from hard drive to the memory. There has to be some management done, right? You have to assign some memory in your RAM where the loader should know that, okay, I have to load it here. Is that understood? So even before loader can load anything, there has to be some management done, right? And that doing that management is basically called as creating a new process. It's an empty process, or it's some generic process, and once that process is created, you will basically then ask loader to copy everything. Only after your process gets created, the loader will copy the bytecode from the hard drive and put it into memory, right? Because up to that point there was no memory before that, right? Is this understood? Let me know if you have any doubt in this. So this is just one way of doing stuff. This is just one way, right? And this is the Linux way. So for creating a new process, so for both of these things, there are separate system calls. For both of these operations, have separate. Again, this is very specific to Linux. So for creating a new process, the system call is fork. And for loading the program, the system call is exec. Again, when we say load the program, it's basically calling a loader. So this is basically your loader code, operating system loader program. And fork is a program which basically creates a new process. Okay. So these two system calls will be used by your UI. So this guy, this particular piece of code will uses combination of fork and exec to run a.out. Okay, so now we'll discuss fork and exec shortly, but is this clear? So when we discussed loading a program into the memory, we had few steps, right? So now that steps, we saw that there was 4.1 and 4.2. 4.1 was that have some memory and copy into that. But then we say which memory then operating system knows. We just kept that question dangling. Now we are answering that. So we'll say that we first create some dummy process, and then we will ask loader to load into that. Hopefully that is clear, right? So now fork system call is used to create a process. Okay. Now we'll get to details of fork system call, right? So I'll just first explain the high level detail, and then I'll go into some little more depth. So consider that this is your UI. Maybe I should be using same color. Which color did I use? Blue one, is it? So consider that this is your UI code, UI or bash shell, right? Again, this is also a program. This is also a program. Then what you did is basically you asked this program to run a.out, right? You requested this particular, instead of directly requesting to the operating system, you requested this particular program to run your file. Why? Because it's convenient, because you don't have to deal with the system calls. This guy will do it internally, right? So once this program receives the request, the first thing that it has to do is basically create a new process. Okay. So note that this is some program. This blue box itself is some program. It means it has a PCB, because it's a program. So it itself will have some PCB, some process control block in operating system, right? Is this understood? Now, when this particular program calls a fork system call, when it will call, when you ask it to create a new run this program, so it will try to create a new process. For creating that, it will make a fork system call, right? When it issues a fork system call to the operating system will create a replica of this process. So when we say this, it's basically caller process. So whichever process is initiating a fork system call, operating system will basically create a replica of that. It will create an exact copy of that. Is this understood? So it will basically, what it will do, it will create a new PCB which is very similar to caller program, caller process. Now if it's UI, it will be creating a separate UI, right? Huh. So there the question is, who is calling fork UI or a dot out? So a dot out, you basically initiated the request for a dot out to the UI, and on your behalf, the UI is calling fork system call. So you asked UI to run a dot out, and then UI is calling fork to create a new process, right? And whenever it creates a, whenever it initiates a fork system call, operating system will create a new process whose PCB will be very, very similar to basically the caller process, which is UI in this case. It's basically the new process that it creates is exact replica of whatever is going on here. Okay. There are few differences. I will get to that. Correct, correct. So it will be replica will be UI or bash cell. That is correct. But why is it created? It's just a mechanism to create a new process, right? It need not to be the most optimal way. This is the way Linux does it. This is the way Linux does it. So a dot out currently it's not in the picture at all. If you see here, we are not at the loading stage yet, right? We are not at the loading stage here. The a dot out comes into picture only at the loading point. It's currently in the hard drive only. It's not here yet. Yeah. So at this moment, we are currently only doing this, right? So everything it creates an exact replica. Only few things are different, right? So what is important for us to understand is that process number will be different because you are creating a new process, right? Even if it's an exact replica, it is a new process. So it should have a different process number. Is this understood? Okay. Okay, so it will create a new process. It will have a different. It will be exact replica. So all other fields, right? At when I'm saying all other fields, it's basically whatever we know at this moment, right? There can be other things also. So for example, the CPU register values that it should be using, the program counter values that it should be using, whatever, right? It will be exactly the same. It will be the exact copy of the process, except the process number might be different. Is this understood? So now we'll see an example in C. Okay. It does mean that UI is creating itself. Yes, it does mean that. Yes, that is the conclusion. It is doing it in more efficient manner than we hope to understand it at this point. But it does mean that it's creating replica of itself. Okay, so now we'll do the same thing in C. So let's write a program in C. So again, you have int main, right? And then here basically, let's say we do int a equal to 1, and then we do a equal to 2, and here we initiate a fork system call. So shell can do it, but you can write a program which can execute fork also, right? That is also possible. Maybe let's make it more interesting, right? Okay. So fork system call, up to this point, we assume that the UI itself is calling it on your behalf, but you can write your own code which can also initiate a fork system call, something like this. This is the code that I have written, right? So then I start running this code. When you start running this code, without writing for, we can click run button, then replica is created, sir. Correct, correct, correct. So that is through your UI, right? But what we want to understand is, right, how exactly we can do it in C also. That is from the understanding perspective, that is what we want to learn. how exactly fork works, right? So this is like the high level detail of how your UI works, right? Now we are drilling again in more depth here. We are going into depth here again. So now we are understanding how exactly this fork works, right? So for understanding that, we ourselves write this particular code in C, right? We ourselves write this particular code in C, and then we see what happens if we run this code, right? That is the objective. Okay. So when, let's assume that this process starts running, right? How it starts running, we don't care. Let's assume that it starts running, right? Let's say this process, again, this will have a PCB and it will have some ID, right? Process ID. Let's call it PID is equal to 11. Yeah, some it may not be the right number or whatever, right? Let's call it, this process is running right now and it has a PID of 11. So it the CPU executes this particular line. It sets A equal to 1, and then it comes here, right? When the moment it comes here, this is a system call, right? This is a system call. So the moment operating system receives this particular system call, it will create a new process, which is the exact replica of this. Okay, so I think I wasted space. Well, let's write it again. I'll write the same code just because, like, with space, right? That's it. So A is equal to 1. Again, I'm dropping all this syntax and all. That's it, right? A is equal to 1. Then child ID is equal to fork. A is equal to 2. So this was like my original program which was running. Okay, so now whenever this system call is issued, again, I will write here. I will not draw the entire PCB. I'll just write PID equal to 11. Whenever this system call is issued, the operating system will create the exact replica of this, like this. Again, A is equal to 1. Child ID is equal to 4. We'll get into child ID again. And then A is equal to 2, right? So note that when I say exact replica, it is basically replica of the running process. So this is the running process, right? So this process has executed this instruction. It is executing. I'm not saying it is execution has completed. It is executing fork system call at this moment, right? It has asked operating system to run a fork system call. So when the operating system creates an exact replica, it means that in this new replicated process, again, this is already executed and this is executing. Is this understood? It is a replica of the running process. It's not like you're copying a file. Just take it and copy paste. It's not like that. This is a running process. When you replicate it, it also means that whatever has happened here is also has happened here. Okay, so when we say, so for example, when this process started running, right? It first ran this particular line. It basically ran A is equal to 1, right? Is this understood? This particular line was executed, right? Then this process issues a fork system call, and now it comes to operating system. Operating system creates an exact replica of this particular process, and again, this process will have some PID 23 or something like that, right? Now, when we say it creates an exact replica, it means it also has an instruction A, which has already been executed. So it's basically like you pause this process, you copy this process into some other process, and now you resume both the processes. So you pause it, you freeze it, you copy whatever it is there in this particular process, you copy it here, and you resume both the processes. Is this understood? It's basically freeze, copy, and unfreeze. Is this understood? Any doubt in this? Correct, kind of a snapshot, correct. So newly created process continue execution for the third line. No, it will continue execution from the second line, because for this guy the execution was not complete, right? So it will start executing from the both of the process will start executing from the second line. It means a equal to 2 has not been executed in both. Correct. That is correct. That is correct. So everybody understood this, right? This line was not completed yet in this original process. It was because it initiated a system call, which is a fork system call, and this line has not been completed. What operating system did was like it basically freeze this process. It created a snapshot of that or replication of that, and then basically it unfreeze both the process. Is this understood? Any doubt in this? Okay, great. Will the second child process again initiate fork? No. Why would it initiate again? Again initiate a fork, right? It is basically so this guy has already in between fork system call, right? So what you can assume is basically this. So this might be easier to understand. So operating system creates a replica and it is about to return. Operating system is about to return from fork. It's about to return from fork. Both the processes will start executing from that particular point. So in this original process, the execution will resume by reading this particular return value. In this particular process, the execution will resume by reading this particular value. Sorry. Is this understood? So the point is this: whenever this fork system call is called, operating system will freeze this particular process, or it will pause this particular process, right? It will create a replica of that. So this is the replica of that process. Is this understood? And it will resume the execution by returning this value. So this returning point is basically the unfreeze point. It will resume the execution of both the processes by returning some value. Is this clear? Okay, great. And again, note that this will have a separate PID because it's a new process. It's the exact replica, but it's a new process. Okay. So note that PCBs are different. Okay, because again, the process number itself is different, so PCBs are different. This guy has a separate PCB. This guy has a separate PCB. And then basically what you do is like both the processes have resumed. Then this will get executed and this will get executed. A is equal to 2 and A is equal to 2. Right. So now only question is that why have we written this, right? Okay. So we'll get to that. Now, whichever process calls the fork, right? It's called a parent process. So in our example, this process basically initiated the system call, right? So this is a parent process. The new process is called child process. Is this understood? Okay. So whenever fork returns into parent process. The fork system call returns process ID of the child process in parent. Okay, so this is my parent process. Like we said, we have created two processes now, and both of them will start resuming by in both the cases the fork will return some value, right? Here it will return some value, here it will return some value. Okay, so in the original process which initiated the fork system call, the value that the fork returns is basically the PID of the child. So it will basically return 23 here. This will be 23. Why? Because the PID of the child is 23. Is this understood? Okay, great. So next point is this. Okay, fork system call returns not process ID, or it returns 0. Returns 0 in the child process. Okay, understand this very carefully. The fork system call was called by a single process, which is this blue one, the parent process. Operating system created a replica. It created a child process, right? Now the fork system call returns in both of these processes, because both the new process is exact replica of the original one. In the original process, which initiated the fork system call, the value that it returns is basically the process ID of the child, which is basically 23. So here it returns 23, and in the newly created process, this will return 0. That's how fork system call works. Is this understood? Okay. So this like completes the first thing, right? Like create a new process. I think exec again, it will require more details. It's better if we cover it in the next class. So I think we can stop for today. First, we will do some problems on fork. Even before going to exec, we'll try to solve some problems on fork system calls, and then I'll explain exec again. Any doubt in today's lecture? Everybody understood what PCB is and what a process is? Yeah. So if hardware interrupt occurs, then it runs, right? Like that is not an issue, right? Why is that an issue? If hardware interrupt occurs, there will be again, it will go to IVT and it will basically run that particular code, right? Yeah, that's not a concern. So if it occurs, it will system will do what it is programmed to do. It will go to IVT and it will basically run that code. Yeah. So depends on what kind of interrupt it gets. And there may be some error. Maybe there is some like big failure or something, right? So if the interrupt is because of some other failure, then system might crash also, right? But that's not a concern in this case. That's what I meant. So question is that PCB have the data structure of every process. I wouldn't say data structure. PCB itself is a data structure that holds information of all the processes. PCB is a data structure, which is basically literally a C structure that holds information of all the process. The fork in the program is library function which implements a system, not the actual system call, right? I think it's a system call itself. It's basically a library function, and ultimately it makes the system call. So it's basically some wrapper over the actual system call again. But the actual system call is also called fork, so why not? Generally, this is a library, because if we go into too low level detail, it will be very difficult to write any code. Question is that means fork will create a replica exactly same, but the execution of both child and parent will be on the fork system call line only. Correct. It will be at the point where the fork returns some value. That's where the execution will resume. The child process is just a variable name, right? I can have T, D, E. This is just a variable name. This is a variable name. I can have X, Y, Z, P, Q, R, S, whatever, right? It doesn't matter. Since fork is just creating the replica, can we say same process can have two process IDs, or they have separate? Again, these are separate processes. A process will only have one single process ID. Every process has only one process ID. This is a replica. It means it's a separate process itself. That's it. Wrapper means basically some library on top of it, right? So instead of directly calling the system call, you write a library on top of it. That is, in computer science, it's called a wrapper, right? So software development. The question is that PCB is stored in OS, stored by OS in main memory where user can't access. Correct. User can't access PCB. It can access PCB through system calls. So for example, user can ask operating system what is the system call of some particular process. That it can do. So question is that fork child process shares all the PCB or some part of it as separate. It has a separate PCB. It's a separate process. So it has a separate PCB. It might have similar values, but it is a separate PCB. It's a new process, right? So it will have a separate PCB. Yeah. Any other doubts? Yeah. So question is, PCB gets created with the process creation, or it is already present in RAM? And this is a design choice, right? So why would you keep it in RAM if there is no process, right? You're just wasting memory. So generally, operating system will create the PCB when there is a request for new process. While creating a new process, it will create a PCB for it. But like, again, that is a choice of the operating system designer. It's one of the most efficient choices, so makes sense. Question is there any role of kernel in fork system call? So like I said, right, the operating system is executing fork system call. It means kernel is executing fork system call. Operating system kernel is basically the code that is getting executed in a system call, right? So yeah, role of the kernel is basically it's the kernel code that is getting executed while creating a replica, right? So yeah, obviously. Okay, I guess like we can stop for today. In next class, we will discuss some problems on fork, and then I'll discuss exec. And after that, we will go to process states and scheduling. Sir, a question is, sir, to speed up the execution process is stored from hard. Wait, sir, to speed up the execution process is stored from the hard disk to the main memory. I didn't understand this question. Okay, so to speed up the execution, process is stored from hard drive to the main memory. Yeah, this optimization and all will again see in memory management, right? So you are right, there are some optimization things going on, but we are not very concerned about this right at the moment. The more important point is that do we understand fork or not? That is the most important part. Yeah, so the question is why to create a new process we need to make a replica. Why can't it be a separate system call? So that is another design. So this is a design choice made by the Linux operating system, right? Whether this is the correct choice or not, that is a very different question. Can this be done in a different way? Yes, it can be done in a different way, right? So then there has to be a new operating system. So we are not asking this question whether this is the right choice. We are just understanding that what exactly it does. So for example, Windows has a very different mechanism. It does not have a fork system call, right? It creates a separate process, which is not a replica. Windows had that support, right? Again, which one is better? We are not concerned about that at this moment. What we want to understand is that how exactly it works. That's it. It's a research question, right? Which one is better? So at this point, we are not very concerned about it. Any other doubts? Okay. So I think so. Reason question is reason for loading program into main memory, because CPU can only execute something which is in memory, right? We saw that fetch, decode, execute. It can only fetch something from memory only, right? So you have to load a program into memory. You cannot directly execute it from a hard drive. It has to be there in memory. That's a hardware restriction. Okay, then I guess see you in next class. Depends on architecture, yeah, but most of the architectures are like that. So fetch, decode, execute happens in memory, right? You can have a separate architecture, so why not? But question is like, is it efficient and it is economical? That is the major question all the time. So that's it.